Hello and welcome to our webinar. My name is Ron Nuttall and I am the Engineered Wood Specialist in the North Central region of the U.S. for the Market Access and Development Division of APA. I will serve as moderator for this session. Our main speaker today will be Corey McCambridge. Our topic today is titled Optimizing Floor System Performance with Engineered Wood Products. Before we start today's webinar, I need to cover some basic housekeeping details. This presentation will last about an hour. Slide handouts will be available in the control panel. All participants are muted to ensure clear audio while our cameras are on at the beginning and the end. They will be off during the session to optimize connectivity. Please submit questions via the question pane. Some will be answered in the chat and others during the Q&A at the end, time permitting. A recording will be available on www.apawood.org in about a week for review or to share with others. APA has represented the engineered wood industry since 1933. Originally the Douglas Fir Plywood Association. About 30 years ago, we became APA, the Engineered Wood Association, to reflect the broader product scope. APA is a non-profit trade association representing manufacturers of structural engineered wood products. We support product testing, research, and quality assurance while educating industry professionals on proper product use. While product testing and member mill certification is an important part of APA, we also have a dedicated field team to assist you. Our engineered wood specialists are located throughout the United States and Canada. Their contact information is available at apawood.org. There will be a lot of information covered today, but all documents are available for free download at apawood.org. I'd also like to note that today's webinar is approved for continuing education credits, including AIA and ICC. About an hour after the conclusion of the webinar, an email will be sent to each attendee. It will include a link where you can get customized certificates of completion. Information provided in this webinar is based on APA's research and field experience, but no warranties, express or implied, are made. APA and its members are not liable for any damages resulting from the use of this information. Users should consult local regulations or a design professional to ensure compliance with relevant codes and standards. APA does not control workmanship quality or usage conditions, so it cannot guarantee product performance or design outcomes. The content is copyrighted and a reproduction or use for AI training requires written permission from APA. Your feedback is important to us. You see a QR code on your screen. Please take a moment to point your smartphone camera at it. A link will pop up taking you to a short survey about this session. You're welcome to scan the code now and complete the survey at your convenience. We'll also display the QR code again near the end of the session. Now I would like to introduce today's presenter, Corey McCambridge, Engineered Wood Specialist for Canada and our Observation Services Lead. Corey has a thorough understanding of engineered wood products and systems for almost 25 years in the EWP industry. In his work for APA, he consults with and conducts workshops for builders, designers, code officials, and other building professionals on best practices for specification, selection, and application of engineered wood products. For those just joining us, welcome to our webinar titled Optimizing Floor System Performance with Engineered Wood Products. And now I'll turn the program over to our speaker, Corey.
Thanks, Ron, and thank you to everyone for joining us today. We're about to dive into today's content, so at this time, Ron and I are going to turn off our cameras to better facilitate our presentation.
Our session today is focused on engineered wood products, specifically floor systems, and how they can help improve performance, efficiency, and durability in residential and non-residential construction. We'll walk through the benefits of EWP floor systems, take a closer look at key products, and then discuss design principles, best practices, and real-world job site examples. Along the way, I'll also share APA's resources and tools that are available to support your work. This course equips participants with the knowledge to identify the key benefits, applications, and sustainability attributes of engineered wood products in residential and non-residential applications. Learners will explore essential design principles such as span, deflection, vibration, fire resistance, and acoustics that influence EWP floor performance. The session also covers best practices for installation, field modifications, and moisture protection to enhance system durability and prevent common job site issues. Additionally, participants will become familiar with APA tools, resources, and technical support available to guide product selection, design decisions, and on-site implementation. All right, enough of the introductions. It's time to dig into our session today. But first, why do we use engineered wood products? Well, when it comes to floor systems, there's 4 main reasons designers and builders often choose engineered wood. First, sustainability. These products make efficient use of wood fiber, utilizing a naturally renewable resource and maximizing yield from every log. Second, predictability. They're manufactured to tight tolerances, so performance is consistent and reliable. Third, performance. Longer spans, flatter floors, and greater design flexibility give builders and design professionals confidence in the finished structure. And finally, waste reduction. Precision manufacturing and design efficiency help minimize job site waste, saving both material and labor as well as disposal costs. Together, these 4 benefits explain why engineered wood continues to be a go-to choice across the industry. So we know why they're a good choice, but what types of products are we talking about here exactly? Well, before we get into design principles and best practices, let's quickly cover some product basics for the following list of engineered wood products that are typically used in, but not limited to, floor system design and construction. We'll begin with structural composite lumber, or SCL. When compared to typical dimension lumber products, these products outperform when either face or edge loaded. The superior performance results from manufacturing processes that align the wood grain, eliminate knots and imperfections, and use dried, layered construction to provide dimensional stability and prevent bowing or twisting. The strength properties of these products are published on a proprietary basis by the individual manufacturer and recognized in their product evaluation reports. The most widely used member of the SCL family is laminated veneer lumber, or LVL. It uses specially selected ultrasonically graded kiln-dried veneers and orients those veneers with the grain running lengthwise. In addition, the veneers are lap joined to create long lengths. LVL is commonly used for beams, headers, rafters, scaffold plank, I-joist flanges, and studs. Parallel strand lumber, or PSL, is manufactured from veneers that are clipped into long strands and bonded together in a parallel formation. Similar to LVL, the grain is running in the direction of the length of the beam member to maximize the bending strength. The strands are cut into lengths that are around 300 times their thickness, or approximately 1/8 of an inch thick by 1 inch wide, and up to 3 to 4 feet in length. This product is commonly used in headers, beams, and columns. And currently, this product is proprietary to one manufacturer. LSL, or laminated strand lumber, is another popular member of the SCL family and is used primarily for beams, headers, studs, rim boards, and stair stringers. Unlike PSL, the strands are not cut from veneers. Instead, this product is typically made from smaller diameter trees consisting of a mix of hardwoods like harvested aspen, poplar, and maple, and the logs are stranded instead of planed into veneers. The length to thickness ratio is around 150 to 1, so strands are typically 1/8 of an inch thick by 1 inch wide and up to 12 inches in length. And finally, OSL, or oriented strand lumber. It's another member of the SCL family. It's commonly used for beams, headers, studs, rim board, and millwork. Similar to LSL, the strands are harvested from logs instead of veneers. However, OSL strands are a little bit smaller than their LSL cousin. The length to thickness ratio is around 75:1, so strands are typically 1/8 of an inch thick by 1 inch wide and between 6 to 7 inches in length. Another popular engineered wood product used in floor systems, Glulam. This consists of wood laminations bonded together with the wood grain running parallel to the length of the member. Although they're available in nearly any depth and are only limited in length by manufacturing and transportation restrictions, Glulam beams carried by local dealers usually don't exceed around 18 inches in depth. These beams are commonly used as roof purlins, ridge beams, floor beams, headers, and columns. The typical width of a glulam can range from 1 3/4 inches to 10 3/4 inches, and they're commonly manufactured from southern pine or Douglas fir. Let's look at SCL, glulam, and select structural lumber and compare the strength properties that control beam design, such as the allowable bending stress and the modulus of elasticity, which relates to the stiffness of the material or the ability to resist deflection. Looking at this table, we can group these materials into 3 categories based on their stiffness: low, mid, and high. Note that both LVL and Glulam offer products that fit into all categories, where LSL and dimension lumber fall within the low to medium strength range. In addition to LVL and Glulam, PSL may also be produced with properties that fall within the high strength range. When it comes to sizing the member, each individual manufacturer of SCL will have specifier guides, which include load tables for their products based on design properties published in product evaluation reports. These are typically located on the manufacturer website. For Glulam members, you may also reference our S475 design guide, which contains design tables for roof and floor applications. With these tables, both a live and total load, including dead load, PLF, would be determined based on a tributary width, which could include multiple floors and partition loads if appropriate. The designer can then select an appropriate beam by looking up the span to determine which beam works best for the live and total load PLF that was determined using the appropriate load duration factors, whether the beam is in a floor or roof application. Additionally, Glulam and SCL beams can be sized using manufacturer or third-party software. There are many third-party software available, and a sampling of those is shown here. A list of standard Glulam layups with their associated design values are typically provided for selection directly in the software. For SCL, you may need to manually enter the design values for the intended product, or be very careful about the product you're specifying. Additional considerations for designers include product availability, available software or literature tools that is designed, affordability, as well as whether the members are proprietary or non-proprietary. Proprietary products typically have specific design values and limitations unique to the manufacturer. Because of this, it may require design time when a substitution is requested, and reference code reports will need to be updated with code changes. Examples of proprietary products include LVL, LSL, OSL, and PSL. Non-proprietary products are manufactured to meet standardized design values provided in a performance standard and code reference design guides. This means that the contractor may choose from a variety of available manufacturer products that meet the reference product standard and strength. Examples of non-proprietary products are dimension lumber and Glulam beams. I-joists are manufactured in 5 standard depths, including 9.5, 11/7/8, 14, 16, and 18 inches. Similar to SCL products, I-joists are proprietary, so design values and limitations must be obtained from their respective manufacturer. Different manufacturers may utilize different flange materials of various widths and thicknesses. Each manufacturer typically has their own proprietary series numbers that indicate relative capacity of the I-joist. Typically, for a given I-joist depth, higher series numbers indicate larger capacities achieved through larger flanges. As noted, each I-joist manufacturer has their own specific series nomenclature, and you can see those here. They also have their own proprietary span tables, which can be found on their individual company websites. When using these tables, it's important to note the design parameters that were used to produce them. Most manufacturers will have span tables for simple span applications as well as multiple span applications. They're generally broken down by I-joist depth, series, and on-center spacing. They are also based on a set of specific parameters outlined in the table footnotes. These include, but are not limited to, live and dead loading that's being assumed, live and total load deflection criteria, floor sheathing performance category and span rating, sealing or no sealing, etc. And these may vary from table to table and for each individual manufacturer. Remember that span tables are more conservative than design software. So in some cases, the software may pass a member that appears to fail in the span tables. If an I-joist is specified in an application that meets the design criteria outlined in the span table footnotes and the specified span, it does not require an engineer seal. A seal is only required for point-loaded I-joists or if any of the design parameters are different from those specified in the manufacturer's span table. Floor layouts produced in design software allow design professionals to change these parameters to suit the specific project needs. There should be a layout for each floor and/or roof, and the design properties should be outlined for each. Additional loading for stairs, tiled areas, kitchen islands, etc. should also be included for each level. Material lists should also be provided for each level, including a hanger list, which will usually specify the fasteners required. Let's shift our focus to wood structural panels, including OSB and plywood, which are manufactured using wood strands for OSB or veneers for plywood. Now for plywood panels, the outer veneers are referred to as the face or back plies. The inner plies can be referred to as the core or cross band plies or center ply. The orientation of the strength axis or grain is very important in the fabrication of plywood to ensure dimensional stability and structural properties. The direction of the grain is oriented in perpendicular directions as the panel is laid up. All of the veneers are bonded together with a waterproof adhesive under heat and pressure. This creates a panel where the veneers work together to form an integral unit. As with plywood, OSB is manufactured with layers with the grain of the strands running in perpendicular orientation to the adjacent layer to ensure dimensional stability and optimal structural properties. OSB is commonly produced in 3 or 4 layers depending on the manufacturing process used at each mill. U.S. building codes require that structural panels for applications in the U.S. comply with either PS1 or PS2 voluntary product standards developed under procedures published by the U.S. Department of Commerce. PS1 establishes requirements for structural plywood and is primarily prescriptive. PS2 establishes requirements for structural wood-based panels, which include oriented strand board and plywood, and is a performance-based standard. Wood structural panels for use in Canada must meet the following standards: CSA 0121 for Douglas fir plywood, 0151 for Canadian softwood plywood, 0153 for poplar plywood, and 0325 for construction sheathing, which includes oriented strand board. In addition, for our Canadian viewers, the 2020 National Building Code outlines the thickness requirements for subfloor panels. Plywood and OSB thickness requirements are outlined in Table 9, 2315-5A as shown here. Note that OSB 01 and 02 grades refer to products that meet the CSA 0437 standard, which is no longer in use. And subfloor panels manufactured to meet CSA 0325 must conform to Table 923.15.5b, as shown here. The most common APA-rated subfloor trademarks can be seen here, starting off with a 19/32 or 5/8 category subfloor panel. Then we have a 23/32 or 3/4 category, and finally 7/8 category. In the US, roof and subfloor sheathing requirements can be found in Table R503.2.1.1 as shown here. All right, let's dig into some design tips and best practices. First step to a quality performing floor is to account for variables that will impact floor system performance. This includes the type of finished floor product being used. Is it hardwood, ceramic, marble, LVT? The use of ceramic and marble flooring will require additional loading where installed, and each will have specific guidelines and requirements regarding deflection of the floor system and smoothness of the subfloor deck. What about kitchen islands, countertops, stone-clad fireplaces, and freestanding tubs, along with any mechanical rooms or special use areas? Many designers will use an additional 50 PSF dead load in these areas or align with manufacturer specifications. Here's an example where the joists work just fine. However, when the kitchen island load is added, the I-joists supporting it fail. This is a perfect example of a floor that will likely experience unwanted deflection and vibration that may lead to cracked tiles in the kitchen area over time. When designed with the proper loading condition, the floor looks like this, where the joists supporting the kitchen island have been increased to a higher series, capable of handling the additional load. If sticking to the same series is preferred, other options include tightening up the joist on center spacing or doubling the joists in this area. Another often overlooked vulnerability is kitchen countertop spaces that run parallel to long spanning joists, as shown here in these examples. So it's not just the kitchen islands, but these other areas. They have ovens, fridges, microwaves. They've got the cabinets and all the dishes and other heavy content inside them. A lot of these countertop areas have granite or quartz on top as well. Design professionals that provide additional loads in these areas can help alleviate floor performance related issues in the future. A very important consideration in floor system design, the span condition. And there are three basic span conditions to consider. The first, simple, where the joist or beam spans between two supporting members, A, B, simple. The second is a continuous, where the joist or beam has three or more supporting members and it runs continuous across those middle supports. And then the final span condition is cantilevered, where the joist or beam has two supports, but it runs continuous across that second support. Here's an example of I-joist used in a simple span condition with only two supports. And here we can see some I-joists in a simple span condition with only two supports in the back, as well as some that are in a continuous span condition here. We can see that dropped middle support. Here's an example of a cantilever span condition where the joist or beam cantilever out over the second support. In this case, the cantilevered members are supporting exterior balconies, but they're often also used to support building offsets. This is what the detail looks like in plan view. Full depth blocking between each cantilevered joist along the support nearest the cantilevered section is critical, as shown here. While most commonly used to address bump outs, balconies, and building offsets, cantilevers can also be used on the interior where a long span, short span scenario exists, as shown in this example. Note that in this option with no cantilever, a special top mount hanger is required to resist the uplift force at the cantilever joist end on the far right. You can see highlighted those uplift forces. When the designer uses a cantilever, as shown here, the hangers along the stair header can be removed, and a simple I-joist to rim board connection detail is used. Blocking is required between the I-joist along the support nearest the cantilever. APA recommends keeping the cantilevered I-joist portion 1/4 of the back span or 4 feet, whichever is less. While APA details can be used for all I-joist products, most manufacturers have additional details specific to their products. For instance, some allow for a cantilever up to 1/3 the back span. We have many generic cantilever details that can be found in our Z725 publication for those interested. So what's better, a simple span or a continuous span? Well, from a performance perspective, a continuously spanning joist will feel stiffer and in many cases span further. If we focus on the top scenario, we have two 9.5-inch 60 series I-joists spanning 16'9" each, one on either side, both of them in a simple span. And note the deflection. In the bottom scenario, we have the same series I-joists with the same loading, same span conditions, everything's the same. The only difference here is that we have one joist running in a continuous span. And note the deflection. Let's take this example, however, the same example here, but we're going to use in this scenario a lesser series I-joist in the continuous span. So you can see that the lower series I-joist is actually deflecting less than the higher series I-joist. All we had to do is run the I-joist in a continuous span instead of a simple span. One important consideration for span conditions is load distribution. In a simple span condition, half of the uniform load is distributed to one support and half to the other. Pretty simple. Now for continuous spans, the uniform load is distributed a little bit differently as shown here. And as you can see, the middle support ends up taking just a little bit more than half of the load from either span. This also means the continuous member will experience a slightly higher shear stress than the simple span members. But that's not typically the limiting capacity for longer spans. Here we see an example of a floor over a garage designed two separate ways. On the left, a dropped glulam beam is used to break up the 26-foot clear span, and the floor can be framed using low series 9.5-inch deep I-joist spaced 19 inches on center, running continuous over that drop beam. And on the right, we have no drop beam in the middle, and the joists are spanning the full 26-foot clear span. In this scenario, the floor is framed with 2-ply high series 16-inch deep I-joist spaced 16 inches on center. So this example shows the value of a continuous span. On the left, we can get a 9.5-inch floor system to work at 19.2, but it also highlights the capability of I-joists on the right, that they can actually span that full 26-foot clear span. Back to this photo. Another thing to consider when selecting span conditions is that I-joists require lateral support on each end. In this case, the simple span joists in the back should have panel blocking installed between them along this support. For continuous spans, panel blocking is not required as long as there is no load-bearing walls above. If the structure is located in a high seismic zone, additional blocking may be required. Any blocking or squash blocking below point loads should match the cross-sectional dimensions of the post above. Here are a few examples of simple spans which require blocking. Imagine how difficult it will be to place blocking between each joist in these situations. This is where the advantages of using a continuous span can help not only improve the performance and efficiency of the floor system, but also alleviate laborious and almost impossible framing details as we see here. Imagine being the HVAC installer and having to run through this point. We're thinking double bulkhead. Even worse, when it can be installed after all that work that someone paid for to install the blocking, HVAC and plumbing trades come in and they have their way with it. As you can see in these examples, they just knock them out. As a general rule of thumb, any blocking that's not supporting a load-bearing wall or that is required as part of engineering design for a diaphragm can be considered lateral restraint-only blocking, and the allowable holes described in this publication can be applied. Here we see the allowable hole sizes as listed in Table 1. Basically, the maximum allowable hole size is 2/3 of the lesser dimension of blocking depth or length, assuming that the blocking member is longer than its height or depth. This tends to happen for mid-span blocking as well. The HVAC installation in this particular model was very streamlined, very well organized. Floor system design called for the use of mid-span blocking in a location where the joists were spanning close to 18-foot clear span. And as you can see, most of this blocking has been removed to accommodate the HVAC system components. Now, this is a great example, a reason to design the floor system such that mid-span blocking is not required, so you can avoid these situations. The floor system performance in this area may be unsatisfactory to the homeowner. Fortunately, this area of the floor system supports the mudroom, which has ceramic tile. Without the mid-span blocking installed properly, this section of the floor may experience excessive deflection, vibration, which may lead to cracks in the tile flooring over time. Consistency of the floor system layout or design layout is another discussion worth having. Consider this basic floor layout with various joist spacings and span lengths. It's important to note that floor areas with different spans and framing conditions can result in areas of the floor performing or feeling different than others. In this example, we see an area with short joist spans adjacent to an area with long joist spans, right next to an area with wider joist spacing, and another area where the joist direction changes altogether. These areas where we need to be cautious of are usually isolated to transition areas as highlighted here, where a change in joist on-center spacing or direction takes place. Design professionals can improve floor performance by paying close attention to these areas. The joist spacing is tighter in areas A and B due to the large span in area B. And this is a great example of how, if not designed properly, the mid-span performance of the floor joists in area A could feel stiffer than those in area B. Now, to avoid this, there's a couple of options worth noting. First, analyze the structural components and provide a more balanced and consistent design option, as shown here. In this balanced option, we've eliminated those points of concern highlighted on the previous slide. Sometimes, due to the nature of the design of the structure, we just can't move these main structural components, and we're forced to design a floor system that is unbalanced like this. So what can we do in these situations? Well, this is when we need to focus on controlling the live load deflection and vibration for areas with the largest span, and pay close attention to other transition areas, ensuring the span rating of the subfloor is not being exceeded, and joist direction changes are limited to areas where they're less noticeable. Two very impactful design parameters that will determine the overall performance of the floor system: live load deflection criteria and vibration control. When it comes to live load deflection, the code minimum, L/360, but L/480 is generally recommended. But what the heck does L/over mean anyways? Well, L represents the joist span in inches. So let's say our largest joist span is 18 feet. Convert to inches, we multiply by 12, we've got a total of 216 inches. As you can see, if we were to use L/360 live load deflection, any joist deflecting 0.6 inches or less would pass design. However, based on my experience, any live load deflection over ½ inch should be raising red flags to the designer. By simply increasing the deflection criteria to L/480 live load, we reduce the allowable deflection in the joist, thus increasing the performance of the floor system. To select the best deflection criteria for your project, simply determine the largest span and run this equation until the allowable deflection meets your needs. Just keep it under ½ inch. Another important consideration is your intended finished flooring material, as these can often dictate your limits. Another key element to floor performance, vibration control. In the US, floor vibration is not explicitly regulated in the model building codes, but in Canada it is, and it has been since 1990. CSA 086-19 section A5452 lists acceptable methods for determining vibration. Most design software will include vibration analysis when Canadian building codes are selected. You'll find that in most cases, vibration governs. We'll get into some examples in the coming slides. I have heard that vibration is something that is currently being considered for inclusion in future US building codes. APA has also studied floor vibration, and we have the following technical notes for anyone that wishes to dive a little bit deeper on this subject. Along with this D720 publication, both of these publications discuss causes and potential remedies for excessive floor vibration. But it's best to account for it in the design stages. Using this information, design professionals can ensure that the floor joists spanning over area B will feel stiff, and the difference between them and those in area A won't be as noticeable. Here's an example where the joists under the kitchen, mudroom, and pantry areas pass in the design software, but upon closer inspection, we find that they're maxed out when it comes to vibration at 100%. Design professionals should pay closer attention to floor performance in areas that are likely to see more frequent heavy traffic, such as entryways, hallways, kitchens, family rooms, etc. What are some possible solutions? Well, the builder or design professional can use a higher series I-joist, a thicker subfloor deck, can utilize mid-span blocking, but can be considerate of HVAC. They could install a directly applied ceiling if there isn't one, or maybe tighten up the on-center spacing of the joists in these areas. Here's another example. The joists under the primary bedroom pass design, but when the member report is reviewed, we'll note 95% vibration, and we're getting close to that ½ inch live load deflection. Joists supporting the great room and master bedroom areas of this home were maxed out at 99% and up to 104% vibration. This builder was dealing with a warranty claim on this particular model. Most software allow the user to quickly pull up member reports for a quick live load deflection and vibration check, so this doesn't take very long to do. Revised layout looks like this, where a higher series I-joist was used to maintain an acceptable level of performance from the builder's perspective. A row of mid-span blocking was added in the simple span area to maintain a similar level of performance to the other joists. You can see that deflection or that vibration at around 86 to 90% is where it is now for the whole floor. Through APA's complementary consulting services, the problem was identified and has since been resolved on a very popular model for this builder. Here we see the recommended connection detail for I-joist blocking panels to I-joists, where a piece of 2x lumber is used to make the connection at the webs. This detail is also our starter joist detail for end walls. Another important element in floor design is subfloor thickness and span ratings. Some of our members produce a 19/32 or 5/8 category subfloor panel with a span rating of 20 inch on center. And this means that no supporting member can exceed 20 inches. Some also produce a thicker 23/32 or 3/4 subfloor panel with a span rating of 24 inch on center. And finally, some of our members also produce a 7/8 category subfloor panel. However, be careful when specifying these panels because some come with a span rating of 32 and some come with a span rating of 24. Now, for this reason, it's really important to reference the span rating of the panel in addition to the performance category. Thicker subfloor decks can help reduce vibration in the floor system. If we look back at this example layout, we note that the joists in area C are at a wider on-center spacing than those in area A. We've got 24 on center and 16 on center. These two areas of the floor will perform slightly different, even though the joists are spanning the same distance. In this situation, the span rating of the subfloor is going to play a significant role in the performance of the floor system here. Many design professionals find that it's best to step down the joist on-center spacing from the span rating of the panel. So, for example, if the panel has a span rating of 24, many designers will step down the spacing of the joist to 19.2. If the panel span rated for 20, many will step down to 16, etc. What this does is it leaves a little wiggle room if any of those joists need to be shifted to avoid interferences from plumbing, HVAC, or even anchor bolts on sill plates. That's what happened here in this example. The joist was shifted left to avoid a plumbing drain, and now the spacing between it and the adjacent joist exceeds the span rating of the subfloor. This can contribute to an uneven floor, increased deflection and movement in this area, and the potential for squeaks and issues with the finished flooring. This is why it's a good idea to leave a little wiggle room, as noted on the previous slide, so that the subfloor span rating is not exceeded. Hardwood flooring is being used. Design professionals should consider the following. The National Wood Flooring Association provides guidance on when to use an underlayment under hardwood flooring. This guide details a single layer system where the underlayment isn't required when the joist spacing is not at the maximum rated span of the subfloor panel. APA recommends using subfloor adhesive in addition to fasteners to help create a solid bond between the subfloor and supporting members. Most span tables assume a glued and nailed subfloor. A reduction in spans is typically required if not gluing. These settings can be altered in most design software and should match what is being done out on site. The advantage of a glued nailed floor system versus nailed only, the composite action of the panel with the supporting framing members. This composite action results in an increase in overall floor system stiffness, but not strength. Also, a glued nailed floor is less likely to squeak than a nailed only floor. APA engineers advise that in a glued nailed floor with tongue and groove edges glued, a 90% composite action can be achieved. In a glued floor where the tongue and groove edges are not glued, 45% composite action can be achieved. And in a nailed only floor, approximately 6% of fully composite action can be achieved. However, in a nailed only floor, this small increase typically diminishes as the wood framing seasons or is subjected to in-service humidity changes. We have the following technical topic, TT036, that provides a design example. For this to work, the framer must ensure that the panels are installed properly. This includes laying down only enough adhesive for a few panels at a time to ensure it does not cure before they're fastened, which can reduce the benefits of composite action. APA's recommended fastener spacing for wood structural panels and floor applications is 6 inches on center along supported ends and edges and 12 inches on center in the field of the panel. It's also critical to keep these fasteners tight to the perimeter, so 3/8 of an inch in from those ends, edges, and corners. These recommendations are often overlooked at the job site, as you can see in these examples. Again, we want to see them 6 inches on center along supported ends and edges, 12 inches on center in the field of the panel, not 21. And again, we really importantly want to see them tight to the perimeter, not 3 inches away, 3/8 of an inch away. It's also important that fasteners are driven into framing members. When they miss, like we see in these examples, it's impossible for the panel to be fully engaged with the supporting member. And in floor systems, this can lead to adhesive curing, leaving gaps between the sheathing panel and the framing member, causing unevenness in the floor system, and can contribute to crunching sounds when walked on. It's the responsibility of the framer and building inspector to ensure that all fasteners are fully engaged with the supporting members and that the correct fastener type and length is being used. Here we see an example of a gap that can occur as mentioned on the previous slide. When fasteners miss framing members or are not in the correct location, or when adhesive is applied and left to sit before the panel is installed, it can cure, causing gaps that can contribute to an uneven floor surface, and crackling or crunching sounds can be heard when the panel is walked on. This is a warranty manager's nightmare, or at least one of them. Failure to follow these guidelines can lead to unwanted panel movement and an insecure connection between the subfloor panel and the supporting member, which can result in panel ridging, unwanted squeaks and vibrations, and an uneven floor appearance, as shown here in these examples. For additional information regarding panel subflooring and underlayment, I recommend the following APA publication, which is available on our website for free download. All of the information in our Z725 publication is generic across the industry. There's another great publication, our E30 floors. Again, you can find this on our company website. And for our Canadian viewers, I recommend our R300 publication. It contains very useful information specific to the Canadian market. Directly applied sealing will also improve floor system performance by increasing assembly stiffness and reducing vibration. It can also contribute to better load sharing and help reduce deflection. Separate span tables for floor systems with directly applied ceilings exist due to the positive impact it has on allowable spans. Designers should be aware of fire-rated assemblies with resilient channels, as this is not considered directly applied. Floors over garage areas may not have a directly applied ceiling if that ceiling is dropped. So just be aware of these scenarios, as it could significantly impact the performance of the floor system. Make sure they're being designed correct. Residential buildings with a basement, a directly applied ceiling will not only improve the performance of the ground floor system, which may allow for a lesser series joist or a wider on-center spacing, or both, but it will also satisfy the fire protective membrane requirements listed in the IRC. APA System Report SR 405 is intended to provide prescriptive fire assemblies for I-joist floor systems when IRC Section R501.3 requirements are adopted by the local jurisdiction, and is available to download from our website. When we look at reevaluating the structural elements, it's important to identify point loads generated by girder trusses and flush or drop beams, and ensure that they're not creating offset loads below which require additional support. We try as much as possible to align our point loads with bearings below. It's also critical to incorporate the HVAC system layout in the floor system design. There are many cases where you have a very efficient floor system layout, but it just doesn't work with the HVAC design. The two plans need to blend and work together. EWPs and dimension lumber products don't work together. They don't work well together in flush conditions due to their different depths and different rates of shrinkage, which dimension lumber products are much more susceptible to. Another great tip: avoid changing joist direction as much as possible. Doing so has the potential to create humps in the floor system, and it creates interferences for flush HVAC systems. And this increases labor and waste. Here's a great example where in the original layout, the column supporting the beam in the basement was offset a rather substantial point load from above. This created the need for a 14-inch LVL in the basement, where the maximum drop beam depth was restricted to 12-inch due to headroom, so the beam had to be partially flush, creating the need for this detail, which added roughly 40 joist hangers and a lot of extra labor. By simply moving the post and pad over to align with the point load from above, the beam in the basement worked as an 11/7/8 and could be dropped. The sooner along in the design process that you incorporate these variables and involve all members of the project team, the easier it will be to conduct an efficient analysis and ultimately select the best floor system design for your and your customer needs and expectations. Here's an example of a home originally designed with dimension lumber. You can see the original layout on the left. The builder was interested in making the switch to an engineered wood floor system and challenged the designer to offer the most efficient layout. As you can see, the total number of joists has been reduced by over 2/3. The cross bridging and strapping have been eliminated, and the amount of steel has also been reduced significantly. Which floor is going to be easier to frame? The same can be said for the second floor. The wider on-center spacing of the I-joist and ability to cut holes in the webs following allowable hole size charts allows for more room for flush HVAC and mechanicals, fewer bulkheads, more open design spaces. Callbacks can quickly diminish any initial savings gained by not following some of the tips we've just covered. After working with many builders over my career, I can say it's just not worth it. Spending a little bit more time up front in the design stages and following through with on-site training for trades is a very smart investment. I hope that you've all been able to take something useful away from this session today. Don't hesitate to reach out if you'd like to discuss any of this information in greater detail. APA is here to help. Throughout this session today, I referenced many APA publications, but I really just scratched the surface. We have many tools and publications related to our member products, which can be accessed via our company website, as shown here. To search for a specific APA publication or simply browse our selection of over 650, either enter a keyword in the search bar located at the top right-hand corner of the main page, or click the Resource Library tab, as shown here. And when you do that, a little drop-down menu with many options will appear. A few I'd like to point out: APA Webinars section. This contains a list of pre-recorded on-demand training sessions covering a wide variety of topics. I'm sure this one will be in there soon. Our CAD Details section contains an ever-growing selection of wood frame construction-related details, and you can download them in multiple formats. And the publication category section, it contains many of the publications that we referenced during this section today are in here. And as I said, many more. There's over 650 publications. This concludes our webinar today. Thank you so much for taking the time to attend. And it's been a pleasure to present to you all. This is a great time to submit any questions in the Q&A dialog box.